Well, in first place, I would like to thank the organizers for the invitation to participate in this very nice conference. And I would also like to thank you, the audience, for staying here until this last talk. So, thank you. Today, I will talk about gravitational radiation in space-time with positive cosmological constant. And this work was done in collaboration with Beatrice von Haag from Radboud University in the Netherlands and Claudio Bunster, also known as Claudio Teitelboim, well, who was in Valdivia at that time, and it's based on this work. Okay, I will start with a brief introduction of how to understand gravitational wave in asymptotically flat spacetime, but the important thing is that it's in the fully nonlinear theory of general relativity. The idea is not to talk about linearized waves as we usually learn in the university, but the idea is to understand the structure of spacetime, in particular near future infinity, when the waves are solutions of the nonlinear theory. So for this purpose, it's very important to understand the BMS formalism that was developed by Bondi, Vanderburg, Metzner, and Sachs in the early 60s. And why? What was the main idea of Bondi? Because suppose that we have a Minkowski spacetime and we have a source here. The source will emit radiation, and at some point the radiation will reach square plus, future null infinity. So the key idea of Bondi was to study the form of the phase space near this region, and to integrate the Einstein's equations starting from the boundary using the information of the wave and all the other conserved quantities as initial data, and the idea was to integrate the equations inside the bulk. So the whole point was trying to understand how the information of the wave is codified near square plus. Now, why this analysis was so important? Because before this works, it was really unclear whether gravitational waves were real or not. At some point, even Einstein, who found the first linearized solution to general relativity described by the wave equation, at some point wrote an article saying that, okay, they possibly they were part of let's say, an illusion of linearizing the equations. But with this work, this problem of this apparent paradox was solved by two reasons. In first place, because no linearization was needed. And in second place, because Bondi also developed or was able to found an equation that described the flux of energy of the waves. So basically, we have flux of energy, and non-trivial flux of energy means that the waves were real. They were able to produce some work and so on. So this formula, Bondi's energy loss formula, is really very, very important. Now this formula depends on this quantity, NAB, which is a symmetric and traceless tensor with two components. This is called the News tensor, and contains two independent components which precisely coincide with the information that of the 2 degrees of freedom of the gravitational wave. Later I will show you how to define precisely this tensor, but this is the important physical object, the object that contains the information of the wave near square plus. In addition, in particular after the works of Sachs, it was clear that the asymptotic symmetry algebra near square plus was not the standard Poincaré algebra. This symmetry was extended by the so-called supertranslation, so in such a way that the symmetry of the spacetime near null infinity is given by the so-called BMS algebra, which consists of the semi-direct sum of Lorentz generators with an infinite number of supertranslations. In particular, the supertranslations can be characterized by a scalar function of the sphere, so it can be expanded in spherical harmonics. So the first harmonic, when L is equal to 0, describe the energy P0. The modes with L equal 1 or 3 describe the 3 components of the linear momentum. And the higher multiple moments describe the so-called super translations. This is the idea. Okay. Now, in recent years, this symmetry has been studied extensively, mainly because due to the relation that was found mainly by Strominger and his collaborators with the soft theorems and the memory effect, and now is also the basis for some of the flat space proposal for flat space holography, in particular Celestial CFT and Carolan CFT. But in my case, and from a very practical perspective, it's important to analyze the symmetries because they play a crucial role when we try to determine what are the relevant physical quantities like energy, angular momentum, and the corresponding fluxes. So for example, if we want to compute the flux of energy, we need to know what is the energy, okay? And this is part of the BMS analysis. Now in the case of when lambda is equal to 0, the gravitational waves have a very important property that in general looks like obvious, but it's not. And it's the following, that in general, at very large distances, as we approach to null infinity, the information of the wave is encoded in this, well, it doesn't work. No, it doesn't work. No, I know, I'm not. Well, okay. Sorry. Let me go back. Okay, the information of the wave is codified in this tensor, which and this term decays like 1/r. So at very large distances, basically the amplitude of the wave goes to 0. So we obtain a Minkowski spacetime plus a small deviation with respect to it. This is well known and is fundamental for the boundary analysis. And by that reason, there is a sort of linearization. So the linearization of Einstein's equation near scribe plus. Also near space like infinity. But now the question is, what happens if we try to extend these ideas when the cosmological constant is positive? Now, why to do this? In principle, because experimental evidence suggests that our universe has a small and positive cosmological constant. So it's very small, so for any practical purpose, it's completely irrelevant, can be neglected, and this is what happens in practice with the current gravitational wave detectors. But in any case, I think from a theoretical point of view, it's interesting to see what changes in this case. If it is possible to define a notion of energy flux, you will notice immediately that this is subtle, because what do we mean by energy in the zither? Okay? And in addition, well, almost everything changes. Even the very basic fundamentals of gravitational waves, what we learn from fundamental waves, changes if we have a positive cosmological constant. In particular, if we have a source here at some point that will emit gravitational wave, the waves will cross the cosmological horizon and finally will reach scribe plus, future infinity, which is space-like. So basically, the idea is to perform, if one wants to do something analog to the boundary analysis, we need to study this region. Now, some changes as compared with asymptotically flat spacetime. In first place, there is no global time-like Killing vector, so this is a problem. And as I say, the boundary now is space-like and is at the future. Another very important difference as compared with the case when lambda is equal to 0 is that the wave field does not decay near the future. We don't have this 1/r behavior. Indeed, for example, for linearized waves, in these conformal coordinates, one can see that the information of the wave is codified in this tensor, which is traceless and divergentless, and that as we approach to the future, when eta goes to 0, the leading term is of the same order of the background. So basically we have Minkowski, the boundary of future scribe plus in the zither space, but the wave is of the same order, does not decay. So this produces a really major change as compared with the asymptotically flat case. Well, but some of these reasons, this story was largely unexplored. I mean, only after this paper, a series of papers by Ashtekar, Bonja, and Kesavan in 2014, from 2014 to 2016, that they were able to develop, let's say, a more consistent framework to try to deal with this. And indeed, they were able to derive the first corrections due to the cosmological constant to the famous Einstein quadruple formula that described the energy flux of the gravitational radiation produced by a quadruple. So it's really very recent. Now, in order to have some intuition, because this will be really the main physical problem that we will find. As I said, in the case of when lambda is equal to 0, imagine that this is the boundary. Of course, it's just a very rough picture. But basically, we'll have the geometry of the boundary and a small deviation with respect to it produced by the waves. So really small waves, because are suppressed by 1/r. But in the case of the zither, as I explained before, it's not the case. So in principle, we can have, I don't know, some merging of black holes can produce a wave. And in principle, the amplitude of this wave does not decay. So at the boundary, will produce, in general, a very huge deformation. Yes? No, never. This is curious because it never decay. For example, let me go back to well, of course, in our real universe, the cosmological constant is so small that this effect is suppressed. But suppose that we live in an hypothetical universe where the cosmological constant is reasonably large enough. In that case, you will not see this suppression of, due to the large distance expansion. Indeed, there is no such a notion of large distance. And it's because, let's say, the amplitude basically is dominated by this term, which affects the very leading order. So really, they do not decay. There is a redshift, all that, but in principle, there will, let's say, if the cosmological constant is large enough, will produce a very large deformation of the boundary.
But it can be perturbative and not decaying?
Yeah, well, yes, but this is, let's say, if you say, okay, it's perturbative, it means that you're assuming that the amplitudes are always small,
right.
And if the amplitudes are small, the deviation with respect to the background will be small. But this is the important physical point, that in general, our main motivation is to study this in the nonlinear theory, so we don't have this assumption, let's say. But of course, in our real universe, will not be the case. By that reason, we're safe. Okay, well, what is the main goal of this talk? Is to try to extend the BMS formalism to positive cosmological constant. So some of the questions that I would like to answer is, for example, what is the analog of the News tensor? Or where the information of the wave is codified in the different components of the metric near scribe plus. Or for example, can one derive an analog of Bond's energy loss formula? I don't know, what means energy is also a problem, but at least some extension of it with lambda. And also, what are the asymptotic symmetries? These three questions are, of course, related. And let me emphasize that this question can also be relevant in other contexts. For example, in inflation, we know that this era is described by nearly de Sitter spacetime. So in principle, could be relevant, or these ideas could be applied in that context. For example, quantum gravity in the Sitter space, I don't know, I don't have nothing to say about that. Or also ADS spacetime with leaky boundary conditions, because basically all these results can be really extended to ADS by changing the sign of lambda. All the expression will allow this kind of this change of sign without problems. So these are some problem one can explore. And there are many works before this that study different aspects of asymptotic symmetries or radiation in the zeta in nonlinear theory, in the nonlinear theory. Sorry. Okay, what will be the main physical assumptions that we will use? Because in the literature there is a lot of confusion. There are many proposals. Really, it's very hard to follow all the possible proposals. So we decided to impose certain conditions that really restrict the problem. The first one, which is generally overlooked in most of the previous works, is that we are going to assume that all the fluxes and charges must be finite. I think this is a very reasonable physical condition, because if we are going to measure, the flux of angular momentum must be finite. If it is infinity, it will make no sense. So this really, this first condition really imposes strong, very strong restrictions on the form of the phase space. Okay. In addition, we want to have a smooth lambda going to zero limit. Why? Because we know that the detectors of gravitational waves work very well without taking into account the cosmological constant. So we do not expect, for example, a huge jump in the flux of energy, for example, if we turn on lambda. Okay? So all the relevant physical quantities must be smooth in this limit, which is not obvious from the form of the Penrose diagrams. If we add a very small lambda, everything changes. So it's really not trivial. And also we expect that for weak gravitational fields, all the expression reduce to what is known in the case of linearized waves around the zeta. In that case, we have the zeta background and everything is more or less under control. Okay. And finally, we expect that our asymptotic condition must accommodate all the known solutions with positive lambda. I don't know, Kerr de Sitter, Robinson-Trautmann solution with lambda, and so on. Okay. Well, we will work using the Bondi gauge, the same, because by many reasons. Technically, all the computation simplifies. And in addition, it's very easy to make contact with Bondi analysis using this gauge. Okay. Basically, here U is retarded time, retarded null time. Okay. R corresponds to the radial coordinate, and XAB denote the two angles of the sphere. And well, let me try to explain a little bit about what's the form of this ansatz. This term V over R, which is here, contains the standard term which goes like R proportional to lambda and R square of the zeta space. Here we have the number 1 of the zeta space, if you want. Here we have the term that contains the information of the mass parameter of the Schwarzschild de Sitter solution. Okay. In addition, I don't know if it works well, but here there is a shift that is also included. And the most important condition is the following. We assume that the leading order of this angular component of the metric is the round to sphere. These conditions is what allows us to have finite charges. In the literature, there are many proposals, and they consider a deformed sphere. And this leads immediately to divergences. So this was our main assumption. When I say finite charges, implies that this metric has to be the metric of the round to sphere. Okay? And in addition, we have this CAB that will contain information of the wave. Let me show you the case when lambda is equal to 0, just to... This is the case of Bondi. So we don't have lambda here, all the terms with lambda vanish, but the ansatz is almost identical, okay? Except by this term with lambda, this one, and this shift. The expression takes the same form as in the case of Bondi. And they also, okay, in the case of Bondi also, the information of the wave is encoded in this symmetric tensor and symmetric and traceless tensor CAB, which is related with the News tensor. The News tensor that I showed you before in the expression for the energy loss formula is the time derivative of this CAB. And in addition, we will, well, in the asymptotic, in the case of Bondi, the flat limit, this is also the metric of the round to sphere. Okay, this foliation is here in this diagram. The blue lines describe the surfaces with constant U, okay? And U, as U increases, one moves in precisely in this direction, okay? And this is what will define the notion of flux. Flux is not in time, because there is no time there, but means that is in this, along this spatial direction, that at the end of the day will correspond to the generator of the dilatation of the three-dimensional space here, scry. And here also the gray lines correspond to the R equal constant surfaces. So we can see that, I think at the batteries, as long as we approach, when R goes to infinity, we approach scry plus. This is what we want. By that reason, this system of coordinates is very useful. The waves comes, let's say, are emitted here and will reach the boundary. But, well, it's a good point. You can also have an observer in principle in this region, yeah, which is causally disconnected, and the waves also will reach scry. And by that reason, as I will show you later, the expression for the energy loss is not manifestly negative, because basically the boundary receives two contributions. One from the observer here that gives, let's say, produce a negative flux, but the observer here, if we move in this direction, will, let's say, will generate a flux in the opposite direction. So we'll have a minus a minus sign in the, let's say, this observer using this only this patch of coordinates, there is emits waves, and one can see that this observer here absorbs waves. This is something, the physical interpretation. By that reason, we do not expect to have a manifestly negative expression for the energy flux. Okay, and another important condition that comes from Einstein's equation, this comes from really from solving Einstein's equation, is that there's a relation between this UA0, which is the shift, let me go back, is this shift, this leading order, which is not present in the case when lambda is equal to, in the case of lambda equals 0. And also it relates, let's say, the shift with CAB that contains the information of the wave. And this equation is very important because this is what contains most of the physics of this. For example, when lambda is not 0, if we have a non-trivial CAB, it will induce, let's say, the information of the wave, which is codified here, will induce, or means that UA will also contain the information of the wave. And this term, doesn't work. And this term is the term that this shift is what modifies the expression of the boundary metric. Okay, when I told you, okay, the boundary metric is the form, this deformation is produced precisely by this term, which is induced due to this new tensor. Okay, this is the way to understand the problem. But when lambda is 0, this is not the case. So really, we have 0 here. So this is the conformal equilibrium equation of the sphere. One can solve this, but the shift does not contain information of the wave. It's just a change of frame. Okay. So this is the most important equation, and the divergences that we will find in the charges will be proportional to this equation. So when this equation is imposed, that comes from of having a leading the sphere in the leading order of the angular component of the matrix, all the divergences will be removed. I will show you this later. Okay, this is more technical, but okay, one has to preserve the asymptotic conditions. These are the Killing vectors. They take a very similar form as in the case of the asymptotically flat spacetime, but the parameters must obey this equation. This comes from the preservation, and also they have some time evolution equations. But what is different as compared with the asymptotically flat case is that now these equations contain information of the wave. So this is very, I don't know how to say this, very weird, because by many reasons. Because basically if you compute the commutator of two transformations, you obtain an algebra that is field dependent, that depends on the radiation field, which is of course very strange, but has to do basically by this deformation. The boundary is deformed, so this information in some way is encoded in the algebra. This seems to be reminiscent of the what is called the lambda BMS algebra proposed by Comper, Fiorucci, and Rosiconi, where they claim that the symmetries in asymptotically de Sitter space is not an algebra, it's an algebra which is field dependent. However, to me it's difficult, it's personal in this opinion, but it's difficult to make sense of a field dependent algebra. What does this mean? And in particular, it creates, immediately you will have issues with the functional integrability of the charges, because the parameters will change at any time depending on the radiation field. So it's really difficult to make sense of this. But fortunately, we were able to show that there is a subalgebra, which is really a Lie algebra, which is spanned by R times SO3. And this R generates precisely translations in U in the retarded null time, so we will be able to define energy. And these are the spatial rotations that allows to define angular momentum. So what does this mean? That in spite of that we have this very strong deformation of the boundary, the phase space is such that this deformation does not affect these two symmetries. These symmetries still remain even after this huge deformation produced by an arbitrary wave. Okay, this is more or less the physics. And with this quantity, we are going to compute the fluxes. Well, here in the article we use the Banach-Brand method, but you can use any method that you want. We also did it in the Hamiltonian formulation and works the same way. But basically, you find two sets of charges, two charges. Let's say the energy. Be careful that energy, I mean the charge associated with these dilatations at the boundary, and angular momentum, which is defined by this. And there appeared a potentially divergent term, which goes like R. So when R is going to infinity, diverges. But it's proportional to this term, which is precisely the equation that I wrote before for the parameters. And also depends on this expression, which is the equation that relates the wave with this shift. So this divergence vanishes, and all the charges are finite. So now we can compute the fluxes. So what's the energy flux? Just using Einstein's equation, one find this expression. So it clearly has many corrections coming from lambda, lambda and lambda squared, and also contain higher order terms, let's say quartic terms here in the field that contain information of non-linearities of the theory. Here the theory is not really linearized near the boundary. It's still non-linear and can be seen from this term. And this is a sort of bond-induced tensor in the case where lambda is non-zero. Okay, and the same for angular momentum. I didn't write the full expression, but it's in the article. So let's perform some consistency checks. The first one is, let's take the lambda going to zero limit. If we do that, we can see here that well, most of these terms vanish, all of this vanish, and here only the first one survives. And this is precisely the definition bond-induced tensor. So immediately we recover the energy loss, bond-induced energy loss formula, and the same for the angular momentum. So this works well at least, and the limit is smooth, as I said before.
Sorry, one question. Could you go back to the last slide? In NAB, the last term, that it's minus lambda over 6,
yes,
gamma AB, how do I distinguish that from the first term after the NAB term on top? Are they similar or not?
This
yes,
term,
this term and with the second term on top.
Yes, because here we have the square of this term. So this term will contribute with a term of quartic order in the fields.
Sorry. Thank you. Yes.
And quadratic also in lambda. Okay, second consistency check. Let's use this to compute the charges of Kerr de Sitter. And hopefully there will be no fluxes, because if you have obtained a non-trivial flux in Kerr de Sitter, means that doesn't work. So basically here we have to consider Kerr de Sitter in standard Boyer liquid coordinates, and we implement an asymptotic change of coordinates in order to accommodate this within the asymptotic conditions. And we found that this mass parameter, this m, this is a function in general, depends on the mass parameter of the solution and also the rotation parameter. In this way, there is a non-trivial shift as expected by the rotation, and this was one of the coefficients of the subleading coefficient in the angular component for the metric, and these are non-zero. So if we compute the energy, we obtain the energy and the angular momentum, we obtain these two expressions. Now, some interesting cross-check is the following. Suppose that I give you Kerr ADS. In ADS, we know how to compute charges without any ambiguity. So if we compute the charges for case ADS, we obtain precisely these expressions, but with a minus sign here. So if we perform a weak rotation, we recover precisely this expression. So at least it's consistent with that. Okay? And you can check also that all fluxes vanish. We also showed that the Robinson-Trautmann solution that describes a nonlinear wave can also be accommodated, but I didn't include it in this talk. Okay, third consistency check, the linearized limit. Now let's remove all the terms of all the cubic and quartic terms in the expression for the flux. Let's say we will only keep the quadratic ones. So this one, and so on. All the higher order terms will be eliminated because we're linearizing the theory. And if we compute the total amount of energy radiated in a certain interval delta U, we obtain this expression. And after some integration by parts and some manipulations. Now, if this is the perturbation with respect to the Sitter metric, and you expand it asymptotically, you can identify this different coefficient with this shift and this quantity, which is called the angular momentum aspect. And if you use our expression, you recover this formula. And this formula was found before independently by Kolanovsky, Lewandowski, and Kruschel, Hoke, and Smolka. It's precisely the same expression. So at least it reduces precisely to what we know in the case of the Sitter space. And also, in the linearized case, of course, there is an emergent SO14 symmetry because this deformation is really small because we're considering small amplitudes. So we recover the full de Sitter symmetry. Perfect, thank you. And the last check, let's consider the case when there is no radiation. So we turn off this CAB, and in this case, there is no deformation of this boundary, and one can construct all the Sitter charges, the full SO14 algebra, with these generators. Okay, and one can show that this generator closes in the de Sitter algebra. So it's precisely what we expected. Okay, let me show you an example, a very simple example, in order to get some intuition of what we're doing. Let's consider a linearized wave, just for simplicity, and the wave generated by a quadrupole. So the simplest possible example. In this case, the solution, if you solve the Einstein's equations, linearized Einstein's equation in Bondi gauge, you find these solutions. This solution depends on two independent arbitrary functions of the retarded times. A and, well, let's say 2 times 3, let's say 6. A and B, and A is associated with the electric sector, the parity even sector of the vector and tensor spherical harmonics, and B is associated with the magnetic sector, the parity odd. Okay, and they basically describe the two propagating degrees of local propagating degrees of freedom that correspond to the graviton propagating in the Sitter. Now, if we use our expression for the total amount of radiated energy, we find this expression. So we see that in the limit when the cosmological constant vanishes, these terms are cancelled, vanish. So we obtain these two terms that contain three derivatives in times. And this is precisely Einstein's quadruple formula, contains the three derivatives of the quadruple moment. Basically these quantities A and B are associated with electric and magnetic quadruple moments. But now we obtain the corrections coming from the cosmological constant. And you can see immediately that, of course, the expression is symmetric if we exchange A and B. It has to be, because both polarization of the graviton basically are equivalent. Now, an interesting example is to see another comment is that one can see in this case, since we were very careful when we solved the equations, was to check that the energy flux is manifestly negative. Basically, because we are considering only the flux in this direction, you see, and it's manifestly negative, which is, I think, is very reasonable. Now, an interesting example, is to see what happens if we interpret this expression from the point of view of ADS. Because as I told you, if we change the sign of lambda, all the expressions are valid for ADS. And this expression are associated with finite charges in ADS. So really everything applies in the same way. But you can see here that there will be a minus sign here in ADS. So basically, I think that the interpretation is that suppose that you have the ADS boundary, and you have some device here in the boundary. So this device partially absorb part of the energy of the incoming wave, and part of it is also reflected back to inside the space-time. Okay, so basically this describe ADS with leaky boundary conditions. So I think it would be interesting to try to understand how to interpret this from the point of view on ADS. But all these quantities can be computed and are finite, they're well defined, and so on. So what is the role that they play in ADS? I don't know. Okay, this is this is all what I'm going to show you. Let me make a brief summary and outlook. What we did, we developed an extension of this BMS framework for positive cosmological constant near square plus for nonlinear generativity without linearizing the equations. We found that symptotic symmetry algebra was R times SO3, and we used these quantities, this symmetry, to define an energy, flux of energy and a flux of angular momentum. And we also found that the information of the wave is encoded in this tensor CAB, or equivalently in this tensor UA, that of course has two components, as it must. Now, what can do with this? Well, in first place, I think it would be useful to try to establish an explicit connection with some previous approaches, some other approaches. For example, there is an interesting proposal by Fernández Álvarez and José Senovilla, where they constructed a sort of generalized pointing vector, and they claim that the information of the wave is encoded in this pointing vector. I think it would be nice to try to make connection with that, and also with the work of Comper, Fiorucci, and Rossiconi, because they considered the form metric of the two sphere. They found some divergences, of course, and they were able to, well, in some way to regularize them. But I think it would be nice to try to make an explicit connection and try to see the origin of these divergences in that case. Another problem that can be explored is in the context of inflation. For example, if there is a memory effect in inflation. This was proposed recently by Creminelli and Vernizzi, that maybe there is an imprint in the CMB coming from the memory effect at the end of the inflationary period. I think could be, with these tools, in principle, this can be studied. And also, what is the role of this analysis and these quantities in the context of quantum gravity in the zeta space? I don't know, but I think this has to be explored. Well, this is what I have to show you. Thank you.
Hello, thank you. Maybe you said this already, but the connection with ADS, wasn't there a very similar story by Pastersky and others last year?
Well, the work of Pastersky was based on this proposal of compare Fiorucci and Russicone. So it's related, well, this is precisely this. I think it would be nice to try to make the connection with that, but one must be careful that in that case there are divergences that must be controlled in some way. I think this is still unclear.
No, so my question was, so are you saying that in De Sitter there is no notion of this cotton tensor story that they have to capture the radiation at the boundary? I mean, in ADS, these leaky boundary conditions are captured by this cotton tensor of the boundary tensor, of the boundary metric, right?
Yes.
But you said that in your formula, just switching lambda to
Yes,
I lambda, you
it's
get
also captured, yes, it's a good question. Let's say the information of the wave is also captured by the cotton tensor at Sky Plus at the future.
Yes.
Because basically, if you consider a conformally flat space, one can show easily that the symmetry reduces to full De Sitter. So it's like to truncate the information of the waves. Okay, if the cotton tensor vanishes. So basically, it's related with that.
No, I guess my question was then what was the mystery is my question. I thought you said that something about ADS you did not understand, but...
Sorry, what's the question?
What was the mystery about ADS?
No, the mystery, I think, let's say we have the ADS boundary here. And we're introducing some sort of device here that we don't know what it is. But this device, if there is an incoming wave, part of the information will be absorbed by this device, and part of the information will go inside back. But what does this mean physically? I mean, of course, it's a boundary condition that we're imposing in ADS. But I don't know, I think it would be nice to have more intuition on this. This is the point.
Okay, thank you.
There we go. Can you say something about how we can see linearizations, stabilization in your formalism? Like, do you know about this constraint that if you consider linear perturbations around De Sitter, all the global charges are supposed to vanish? I'm guessing those charges aren't quite the charges that you're considering. Is there a relation between that statement and your charges?
I mean, I'm not sure if I understand the question, but if you want to linearize, okay, I didn't have the, let me see. Suppose that we want to linearize the expression. This is the expression for the Killing vector, asymptotic Killing vectors that must satisfy. So we can see that these terms are of higher order in the perturbative expansion because we have the wave field here. So basically, this term will cancel because of our second order, and this is the conformal Killing equation for the two-sphere, which has whose solution is precisely the Lorentz group. You see? And this is basically how immediately the symmetry, the De Sitter symmetry emerges naturally, because let's say what kills the De Sitter symmetry are these higher order effects.
Okay, but just so I understand, the charges that you're defining, if I consider integrating it over the entirety of Scry plus, they do not vanish, is that right?
No, the charges do not vanish.
For linearized perturbations, they don't vanish?
No, they don't vanish. No.
Okay.
They have non-zero. Yes. No, they're non-zero. And this is what I showed you in the last example. We compute a linearized wave in De Sitter and has a non-trivial flux.
More questions? If there are no more questions, then maybe we can thank all of today's speakers again.